Hi everyone, this is Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the iron carbide diagram and its development of microstructures in these phase diagrams. So in this session we will discuss about how the iron carbide diagram is drawn with the help of these Gibbs phase rule, and also during the cooling process, what are the different types of microstructures are being developed inside these iron carbide diagram? Is it not? Since we are cooling the system slowly from the liquid, it converts to solid state. So during this conversion from the liquid to solid state, so it has its own type of microstructure. During the travel from the liquid state to solid state, at each state there is some development in the microstructure during this cooling process. So that also we'll discuss in this session. And firstly, we'll see what is this iron carbide diagram of the phase diagram. Now, in the previous sessions, we have discussed about different types of alloys and its phase diagrams. Like example of water, we have seen how to draw the phase diagram, and also we have discussed about the sugar and water, its different phases, how to draw the phase diagram, and also some of the copper and aluminum. Also, we have discussed about the how to draw the phase diagram. And these phase diagrams we are drawing with the help of the phase rule, that is the Gibbs phase rule. So, what is the Gibbs phase rule? We have discussed that is P plus F equal to C plus N. Here, P refers to the number of phases, F is the number of degrees of freedom which are externally controlled, and P plus F equal to C plus N. What is C? Number of components present in the system. So how many components are there? So if you see in this example, we have iron and carbide. So two different phase components we have. So we have to take as components as 2. And of course, the last term N refers to the number of compounds which are non-variables. Okay, which are non-variables like the pressure. Okay, so temperature and composition can be variable. Pressure we are taking it as a constant value. That's why the N value we are taking it as 1. So there is the Gibbs phase rule we have to follow in order to draw the any type of phase diagrams. We have to follow the Gibbs phase rule. So this Gibbs phase rule not only gives the relation between the number of phases, number of components, and number of externally controlled variables, but also it gives the additional information of how the inside the alloys are being changed. I mean, their characteristics can also be studied with the help of these phase diagrams. So that's why the Gibbs phase rule is very important in drawing the phase diagram, and also the relation between all these 4 parameters can also be calculated with the help of this Gibbs phase rule. Now, from the Gibbs phase rule, we have discussed yesterday how to draw the phase diagrams with respect to x and y axis. X axis represents the composition and y axis represents the temperature. Okay, so this x axis has a variation of composition from 0 to 100, and again if 2 components are there, we have discussed that 2 components at any point, if you see, it should be 100 weight percentage. That means if 2 x and y are 2 components are there, if x starts with 0 and y starts should be 100 percentage, and this x, which since it is starting with 0, it has to reach to 100%, and from y, since it is starting to 100, it has to reach to 0. So that is how you have to balance the composition at any point. If you see, it has to be a 100 weight percentage of the total compositions of the 2 components what we are taking. And coming to the y axis, we have the temperature scale, which is in degree centigrade scale. So if we raise the temperature, we will see what happens to the metal or the alloys what we are considering, whether it is in the liquid state or solid state, or any type of liquid and solid state also, the combination. So this y axis refers to the temperature, so that it gives the information at some particular temperature what is the phase of that particular element, and also it gives the information about the which phase this element is being present. Okay, so that is how the importance of these x and y axis corresponding to the any phase diagram with the help of our Gibbs phase rule. Now we'll consider the famous example of the iron carbide diagram, and how this iron carbide diagram is varying its different phases with respect to the x and y axis, that is the composition as well as the temperature. Okay, so if you see this iron carbide phase diagram, the pure iron upon heating experiences two changes in the crystal structure. So what is happening here, whenever you heat a pure iron, so this pure iron experiences two types of crystal structures before it melts. That means you take a solid component of this pure iron. This pure iron has to be heated. Okay, so what is happening? This pure iron slowly converts to a melting state. So during this melting period or before it reaches to the melting state, what is happening? This pure iron is experiencing two types of crystal structures. Okay, so two types of crystal structures are being observed or being experienced by this pure iron when you heat the metal. So what is happening at room temperature? At room temperature, the stable form of this iron, pure iron, will be in a ferrite form. Okay, if you see this line, pure iron at room temperature, at stable conditions, it is in the form of a ferrite, and which is having a BCC type of crystal structure. Okay, body centered cubic structure, crystal structure is having for the pure iron at normal temperature, that is at the room temperature. Now slowly this is called as a ferrite. Okay, at normal temperature, the pure iron, when upon heating, it is converts into BCC. It is having its own body centered cubic structure, and that form is called as a ferrite. Now slowly what happens, this ferrite, whatever the ferrite is there, this experiences a polymorphic transformation. So polymorphic transformation is nothing but which is having different forms, which occurs in different types of forms. That's why this pure iron has a different types of crystal structures during the melting process, during the heating process. Now at the initial state of its room temperature, this pure iron has a BCC type of crystal structure, which is called as a ferrite. Now this ferrite, slowly if you heat at 912 degrees centigrade, at this temperature of 912 degrees centigrade, this ferrite, which is having a BCC crystal structure, slowly converts to FCC crystal structure, that is the phase centered cubic structure, and this system is called as an austenite. Okay, this ferrite is slowly converting into austenite, which is having an FCC crystal structure at 912 degrees centigrade. That means at initial state of normal temperature, this pure iron has a BCC type of crystal structure and has a ferrite type of crystal structure inside the body. Now slowly upon heating at 912 degrees centigrade, this BCC is converting into FCC and has an austenite type of crystal structure. So that is the development of the crystal structure. So our topic is the iron carbide diagram and development of crystal structure during this transformation. So during this transformation of the heating of the pure iron, what is happening here? The microstructure is also being converting from the ferrite to austenite because we are heating the element. Okay, slowly it is converting from ferrite to austenite at 912 degrees centigrade. Initially it is at room temperature, it is a ferrite. Slowly upon heating, it is converting to austenite at 912 degrees centigrade. That is from BCC to FCC. Now if you further heat, what is happening at 1394 degrees centigrade? What is happening? Whatever the austenite is there at 912 degrees centigrade, which is having a BCC type of FCC type of crystal structure, slowly this FCC is converting into again to BCC. So it is a complete cycle process. So the phase centered cubic structure is slowly converting into body centered cubic structure all. So that, like this FCC reverts to the BCC. Again it is coming back to its original type of crystal structure, and which is known as a delta ferrite. Okay, initially it was a ferrite, then austenite, then again delta ferrite. So this is how there is a development of the microstructure during this heating of your pure iron. So at what temperature you are getting this delta ferrite? Means at 1538 degrees centigrade you are getting this delta ferrite. So initially at room temperature we are having a ferrite type of crystal structure, and slowly upon heating to 912 degrees centigrade, this ferrite is converting into austenite at 912 degrees centigrade. Now still if you heat up to 1538 degrees centigrade, this austenite is converting into delta ferrite. So this is how there is a change, there is a transformation of the pure iron upon heating of the element. Now if you see the phase diagram, so we have the x and y axis. So x axis refers to the composition and y axis refers to the temperature. So here your temperature which is in degrees centigrade, it starts with 400, reaches to 1600 degrees centigrade. Now this is the composition percentage along the x axis. So you have a iron composition, that is the pure iron which exists at the 0. This is the pure iron. Slowly, if you increase the percentage, it reaches to cementite. So generally, whatever the phase diagrams we are observing, the composition weight percentage will be reaches to 100. But if you see here, it is closing up to 6.70 weight percentage only. Why means why this is very important in the iron carbide diagram. Okay. Now, generally the iron carbide diagram is divided into two portions. One is the rich iron, another is rich graphite. We have two portions in this iron carbide phase diagram. Okay, so one we are considering as rich copper, rich iron, another is rich, that is carbide, which is called as a graphite. Okay, but we are not concentrating for the rich carbon content, that is the graphite. So up to the formation of cementite, that is the iron to iron carbide. So up to what percentage it is converting into from iron to iron carbide. So that's why this is called as iron carbide diagram. So from 0 to 6.7 weight percentage, so it's from 0 to 6.7 weight percentage of carbon, we are getting the iron to iron carbide conversion. So that's why this is called as a iron carbide diagram. Okay, so that's why we are stopping this carbide diagram up to 6.7 weight percentage of carbon. Now if you further increase to 100 percentage, so what is happening here? Since we have rich percentage of carbon, so this is completely 100 percentage of graphite. So at this point, when it reaches to 100 percentage, we are converting into graphite. But we are not discussing about the graphite here. We are considering only about the iron, which is converting into iron carbide. So that's why it is called as the iron carbide phase diagram up to 6.70 weight percentage of carbon. So this is what you have to remember while drawing the iron carbide diagram. In any other type of phase diagrams, we are taking this composition percentage up to 100 percentage. Up to 100 percentage we are reaching and we are drawing the phase diagrams. But in case of this iron carbide diagram, we have to restrict up to 6.70 weight percentage only. Why means up to this point only we are converting this iron to iron carbide. That is very important. So, and how we are deciding that whether it is coming to 6.70 only with the help of the phase diagrams only. So once this pure iron, it has two different types of crystal structures, and also it has a pure iron at 0 initial state, and slowly if you increase the percentage of carbon content, it is converting into a graphite. Okay, so this is the development of the microstructures inside the material, what is happening with the rise in the temperatures or with the additions of the other types of carbon content. So all these we are getting the information with the help of these phase diagrams only. That's why these phase diagrams are very important, and from the basis of the Gibbs phase rule, we are trying to draw these phase diagrams. Now this is how You have to draw the phase diagram for the iron carbide diagram from 0 to 6.7 weight percentage. So this is very important while drawing the iron carbide diagram with the help of these compositions. Now again, we have to see what are the different phases are present inside this iron carbide diagram. How many single phases are there? How many double phases are there? We have to find out. And again, if you want to know the composition at any point in the any phase, directly we can drop the horizontal and vertical lines and find out the composition as well as the temperature. And also, if you want to find out the composition along the dual phase, that is the double phase, you have to use a Thailand process. So in this case, if you observe here, this is the austenite which is having a single phase. Suppose I want what is the composition along this point A. So this is the example. To find out what is the composition at this point. So what I have to do, since first I have to check whether it is a single phase or a double phase. Now first it is a single phase. So if it is single phase, directly I can draw the horizontal lines as well as the vertical lines along the composition as the percentage. Now if I want to know the percentage at point A, so what I have to do, I have to draw these vertical and horizontal lines, and at this point exactly I am getting 1 weight percentage of carbon at what, almost 1180 at 1180 degrees centigrade. This is how you will calculate the composition as well as the temperature along the point A if it is a single phase. Now we'll take the another example. So alpha gamma plus Fe3 or alpha plus L. So this point will take. Now I have a point B. I have to locate the position of the point B. So what I have to do, this point B is in a double phase, is it not? So double phase means we have to use a tie line method, and this tie line method has to draw in between the two phases which passes through the point. So how to draw? I have to take a line which has to connect these two phases. I am connecting these two phases which connects the point B. So I am tying a line at these 2 points. So that's why it is called as a tie line method. We are tying a line between the two phases. That's what it's called, tie line method. And we are trying to find out what are the compositions as well as the temperatures. Now I'll draw a vertical lines along the compositions at these 2 points. So that is B1 and B2. Sorry. So I have 2 points B1, B2. B1 refers to the point of one phase. So if I see the composition at this point, it is almost 1.3. So B1 refers to 1.3 weight percentage, 1.3 weight percentage of carbon at what is the temperature? Like this you have to see. So that is 1394 degrees centigrade. Similarly, if you see the point B2, it is almost 3.3. So B2 will be 3.3 weight percentage of carbon at, again the same we will not get the same because the line is coming somewhat here. So somewhere here you will get So that is at 1300 or 1250, maybe around 1250 degrees. So like this, you have to write the compositions of the two different points along the two faces. Okay, so that is the method you have to use while drawing the phase diagram for the two phase or single phase. That's why it is very very important. If you want to know the composition at any point in the phase diagram, first of all you have to know whether in which phase the point A or any point is lying. So initially you have to check the point which phase it is lying. So if it is a single phase, it is very easy. Directly we can drop the verticals and horizontal along the composition and the temperature line, and you can get the information directly. But the same point, if the point is lying in the two phase region, then you have to use a tie line method. So tie line method, in the name itself you have the tying a line in between that point. Okay, we are drawing the line which passes to the point B or A, and it has to connect those two faces. So we are drawing the line like this, and we are getting the two compositions of the B1 and B2 with respect to temperature. So this is how you have to find out the compositions along any point in the phase diagrams with the help of the tie line method if it is a single phase, or just directly dropping the horizontal and vertical lines if it is a single phase. So that is about the find out in the composition. Now coming to the next point, the composition axis in figure extends only up to 6.708% of carbon. So this is very very important. So as we discussed, we are restricting this phase diagram up to 6.708% of carbon only. Why? Because if you go further, it will convert from the carbon to the graphite rich percentage of carbon. If you increase the composition of the carbon content, what is happening? This iron is converting into graphite. So that we are not considering into in this phase diagram. So up to 6.708% only of carbon, this concentrations of the intermediate compound is called as a cementite. So this compound is called as a cementite, that is Fe3C. Iron carbide is nothing but it is a cementite. It is a cementite which is formed up to this 6.708% of carbon, which is represented by a vertical line on the phase diagram. Of course, this is represented by the vertical line which is seen in the phase diagram. Now the iron carbide system may be divided into two parts. So as I said, this iron carbide is divided into two parts. Up to 6.70 is one part, up to another from 6.70 to 100% it is another part. So up to 6.0, what is happening? It is having a rich iron portion. So it is a iron rich at this point. The another is which is not shown, which is having the composition of 6.7 to 100 weight percentage. It is pure graphite. So we have two portions. One is the pure iron and another is pure graphite. So this pure graphite we are not considering, and pure iron up to 6.70 weight percentage of carbon we are taking, and this is from 6.7 to 100 weight percentage of carbon. Like this, we are splitting this iron carbide diagram into two portions from 0 to 6.70 and 6.70 to 100%. So this is how you have to draw the phase diagram. Now in practical things, what is happening? All steels and cast irons have carbon content which is less than 6.708% of carbon. So what are the steels we are taking into consideration, or what are the cast irons we are taking into considerations in daily practices, which has a carbon content which is less than 6.70. So therefore we considered only the iron carbide system only here. So why? Because in the daily applications or the practical applications, whatever the steels or whatever the irons or whatever the cast irons we are taking into considerations, these have a carbon content of which is less than 6.708%. So since it is having very less composition percentage of the carbon, up to 6.70 only. That's why we are restricting our iron carbide phase diagram up to 6.70 only. Okay. Now, what are the phase diagram we are showing here? This appropriately labeled to Fe3. So the name itself, Fe3 phase diagram is iron carbide, that is iron to cementite up to 6.70 only. So that's why the name also became like this only, iron carbide diagram. It is not telling that iron graphite phase diagram. So iron carbide phase diagram means up to 6.70 only. It is stop. Don't draw the phase diagram up to 100%. So the conventional and convenience dictated that the composition will be expressed in terms of weight percentage rather than weight percentage of Fe3. Okay, so the convention what we are taking into consideration while showing the weight percentage of carbon content developed in this, so we'll write it as weight percentage of carbon. So this is expressed in terms of weight percentage of carbon. If it is a 100 weight percentage of carbon, then it is a converts to graphite. But since it is up to 6.70 weight percentage of carbon, that's why it is called as a cementite. That is Fe3C carbide. Okay, cementite. Again, the carbon is an interstitial impurity in iron and forms a solid solution with each alpha and delta ferrites. So what is happening? The carbon, whatever the carbon is there, it is an interstitial impurity. Interstitial impurity is nothing but in between. Because of that impurity, it changes its orientation. It converts from one position to another position. So because of that impurity, what is happening? Whatever the impurity in the iron is there, it tries to forms into a solid solution with each of alpha and delta ferrite with austenite, which indicated as alpha, delta, gamma as single phases in the field. So if you see here, observe clearly in the phase diagram, you have the alpha, delta and gamma. So these are the three single phases. How it is being converting from one to another. Initially we have seen that first you have a at room temperature, the iron has a ferrite. That is the first one what you are seeing here. At room temperature, I am showing it like this, ferrite here, 1 and 2 austenite. When you increase the heat, so this is the second thing. And the third one is what? Gamma ferrite. This is the third one. So from BCC to FCC, again from FCC to BCC. So this is the transformation of the crystal structure during the heating of the pure iron from the room temperature to around 1592 degrees centigrade. So this is at room temperature, suppose 27 or 28 degrees centigrade, and this is at 912 degrees centigrade. So like this, and this is 1592. So it is converting its microstructure with the help of the transformation of the temperature. And these are, of course, we have the three different fields of these pure iron from ferrite to austenite, from austenite to again delta ferrite. So this is the transformation of the pure iron with respect to the temperature. And of course, these are the crystal structures, changes in the crystal structures at different intervals of temperatures what we have. And now in the figure, if you see, in the phase diagram, you see the BCC alpha ferrite, that is the first one, the BCC alpha ferrite, which is having how much weight percentage? If you want to know, at this point, it is having a 0.022 weight percentage at what temperature? At 727 degrees centigrade. So this is the complete line of the 727 degrees centigrade. At 727 degrees centigrade, we have a alpha ferrite which is having a 0.022 weight percentage of carbon. So very less carbon content. That's why it's called as a pure iron. So at this point you have a pure iron at this point of 0.022. Now the solubility limit. So we have discussed about the what is the solubility maximum solubility limit. That means whatever the solute is there which solves in the solute, okay, up to certain extent only it will be soluble. So after that, if you still add that solute into the solvent, it won't solve. That is the maximum limit. So it is reaching its complete solubility limit. After that, further if you add also, it will not dissolve. So in the same case also, it is also having the solubility limit. So this is the solubility limit which is having. So every phase diagram will have the solvus line and solvus line. So this we have to identify which is having the solvus line and which is not, which is having a solvus line. So in this iron carbide also, this is a solvus line and this is the solvus line. So every phase diagram will have these types of solvus and solvus lines, and we have to identify which are the solvus and solvus line with the help of the maximum solubility limit curve. So with the help of that solubility maximum limit curve, we are identifying the solvus and solvus lines. Now, how this is, there is a transformation of these crystal structures one by one we will see. So development of microstructures in the iron carbon alloys. So phase changes that occurs upon passing from the gamma region into the alpha plus Fe3. So how we are transforming this microstructure from one phase to other phase means these changes occur upon form from gamma to alpha plus Fe3. So like this. So it is changing from one phase to another phase. So because of change of the one phase to other phase, we are getting this transformation of the or the development of the microstructure. So if you see this example, we are considering an example at 0.76 weight percentage. So at this exactly at this point of 0.760 weight percentage of carbon, as it is cooled from the room temperature within the alpha region at 800 degrees centigrade. So what is happening? So it is beginning at a point A in the figure and moving down to vertical axis. So like this, it is slowly coming down like this cooling. So upon this cooling, there is a transformation of the microstructure from austenite to alpha plus Fe3. So now if you see exactly, you can see here from this changes in the microstructure. So this is the point what we have. This is another point what we have. So at point A you have one phase, at point B you have another phase. Okay. Now if you see at point B, it is completely of gamma. You have the more concentration of gamma, and coming to slowly it is, if you see the another phase of alpha plus Fe3 here. So what is happening here? You have a combination of alpha plus Fe3. That is the ferrite and cementite you have. Both the ferrite as well as the cementite you can observe in this. And coming to here, you have completely austenite. So this is completely austenite. And here you have ferrite and cementite. So this is how you have the different transformations of the microstructures or the development of the microstructures during the cooling process. Only from the cooling process only you can observe the different types of microstructures. So from the liquid state, if you try to cool the system slowly from the liquid state, it converts to solid. So during the transformation from the liquid to solid, there are so many developments of the microstructure. So this is one of the example what we are considering at 0.76 weight percentage of carbon. So exactly at this point you have 0.76 weight percentage of your carbon. So at this point, if you take 2 points, at point A you have completely austenite type of microstructure, and if you take the point B, and again this point is very important, 727 degrees centigrade, it is converting from one phase to other phase. So this is the boundary line, and coming to after crossing that boundary line, if you see at point B, it is having the complete different structure of ferrite and cementite. So this is the different transformations or the different developments of the microstructures during the cooling of that curve at 0.76 weight percentage of carbon. And this is called as a eutectoid temperature. So at this point, this is called as a eutectoid temperature. And initially the alloy is composed entirely of the austenite phase. So whatever the thing you are seeing here, it is completely of austenite phase, which is having the composition of 0.76 weight percentage of carbon. Exactly, if you see here, for this at 0.70 weight percentage of carbon, exactly it is completely filled with the austenite only. This gamma refers to complete set of austenite. So this austenite, the gamma. And as the alloy is cooled slowly, if you are trying to cool their system, there is no changes will occur up to what point? Up to eutectic temperature, that eutectoid temperature. Up to this point of 727 degrees centigrade, there is no change. No change in the microstructure. But once it crosses that boundary, that is the eutectoid temperature, slowly this austenite is converting into the ferrite plus cementite. So that is how you're seeing. So as the alloy is cooled, no changes will occur until eutectoid temperature, that is the 727 degrees centigrade. So upon crossing this temperature to point B, the austenite transforms. So what is the austenite available above the 727 degrees, that is the above the eutectoid temperature? There is no transformation in the austenite. Once it crosses that eutectoid temperature, this austenite will transform into the other form of the microstructure. So what is that? The microstructure of this eutectoid steel that has slowly cooled through the eutectoid temperature consists of alternating layers or lamella. So if you see this clearly, what is happening? You can see this, which is having that alternative layers, which is having the two different things, that is the alpha and Fe3, that is the cementite and the ferrite. So combination of ferrite and the cementite are in terms of the alternate layers which are being formed during the transformation from the austenite to the eutectoid temperature. So after crossing that austenite, the eutectoid temperature, this austenite will be transforming into the cementite and ferrite, and this is called as a pearlite. The combination of both alpha as well as the Fe3 is called as a pearlite. So this refers to the pearlite. That means the development of the microstructure, initially it was the austenite, and this austenite after reaching up to eutectoid temperature, there is no transformation. So once it crosses that eutectoid temperature, this austenite is slowly transforming into a pearlite, which is a combination of the cementite as well as the ferrite. Next, if you see the microstructure, the photographic view of this eutectoid steel, which is having a layer by layer, alternative layers. So this is the thing you can see clearly, that is the pearlite, which is existing like a grain system, which is in terms of colonies, which is arranged the layer by layer, alternate layers of the ferrite as well as the cementite. So all these white patches, what you are seeing, is called as cementite, and this black patches is called a ferrite. So this is the micrographic view of the pearlite type of microstructure, which can be seen after the eutectoid temperature. That is, after 727 degrees centigrade, you can observe this type of pearlite thing in the microstructure. So this is the development of the microstructures, different types of microstructures. Now if you see in this figure or the phase diagram, you can clearly see what is the transformation of the microstructure. So initially it was austenite. You can see the solid things, and which is having very less percentage of carbon, the black dots. Now after reaching up to 727 degrees centigrade, there is no transformation in that microstructure. Now after crossing this microstructure, after crossing this eutectoid temperature, eutectoid. So this point is called eutectoid temperature, that is the 727 degrees centigrade. Up to 727 degrees centigrade, there is no transformation in the austenite. After crossing that 727 or the eutectoid temperature, this austenite is slowly transforming into the pearlite, which is a combination of the ferrite as well as the cementite. So this is how you have this. There is a solid portions or the structures of the microstructure of the austenite, which is shown as gamma, and here after crossing the eutectoid temperature, slowly this is transforming into ferrite and the cementite. So this is the microstructure view of the pearlite. And if you see the hypoeutectoid, you have seen the eutectoid temperature, that is at 727 degrees centigrade. You have the eutectoid temperature. So what is the hypoeutectoid alloys? Means microstructure for iron carbide alloys having other than eutectoid compositions. That means other than eutectoid compositions, then that type of system is called as a hypoeutectoid things. Now consider a composition of C0 to the left of the eutectoid between 0.02 to 0.76. So we are considering after that 0.76 is called eutectoid. So in between 0.022 and 0.76 weight percentage of carbon, then that type of systems are called hypoeutectoid alloys. So cooling alloy, the composition represent that moving down to the vertical line. So if you see here exactly, so before we are taken at this point, that is the eutectoid temperature. Now we are taking the alloy in between the 0.022 and the 0.76, then that type of system is called as a hypoeutectoid. So at this point, if you see here, so this is the line what we are taking. Earlier we are taken here as x dash, that is the eutectoid temperature. Now we are discussing about the hypoeutectoid, means the line between that 0.022 and 0.76 weight percentage of carbon, then that type of system is called as a hypoeutectoid. And here also, what is the transformations of the microstructure we can see here. Initially at point C, if you see, it is completely filled of austenite. Wherever you see, we have the complete austenite type of structure. Now slowly this point, though it is above this 727 degrees centigrade, but it is having some portions of this Fe3 cementite. So that's why you have the some portions here, the red spots you can see. That is, though you have high rich percentage of austenite, but some percentage of Fe3 is also available at this point B. Now coming to the point E, again if you have rise in the percentage of Fe3, so that's why you have a dark portions here when you compare with the point at the above point. Now if you come down to that 727 degrees centigrade, you have again combination of you have the pearlite and Fe3 and alpha plus Fe3. All these things you can observe in this phase diagram in the hypoeutectoid alloys. So you have total 4 different portions or 4 different points in this. Above the eutectoid temperature, that is the 727 degrees centigrade, you have 3 different types of microstructures which are available. And coming to the 726 below to the temperature, you have the complete transformations of the microstructure. So this is how there is a developments of the microstructures in the iron carbide diagram, and these we have to study in order to know what is the functioning of what are the characteristics of each type of element during these transformations from one point to another point. And depending upon the compositions of these ferrite, pearlite, we can decide the exact applications of the material. So that's why the material selection can be done when you know the physical and chemical properties of the material and also the different types of microstructures. If you know, then it is very easy for us to apply the material to the required applications. So about 875 degrees centigrade, the point C, the microstructure consists of completely gamma phase. So what we have seen here in the previous phase diagram is having complete type of alpha gamma phase, and slowly upon cooling it is having the combination of Fe3 with gamma, and coming to the other point, third point, it is having a more percentage of Fe3 with the gamma, and coming below the 727 degrees centigrade, you have the rich portions of the pearlite with the gamma particles. So this is how there is a development like this. So this is the microstructure view of the austenite, and of course again you have the very less percentage of carbon content here, the black dots what you are seeing, and this is the difference of the microstructure when you see there in the eutectoid alloys. In the eutectoid alloys, what we have a colonies like this, alternate layers we have, layer by layer we have in this we have a perlite for the case of eutectoid. Coming to the hypoeutectoid, there is a complete transformation of the microstructure in which you have the perlite and proeutectoid as well as the ferrite. So these are the three different types of microstructures you can see through the microstructure of these hypoeutectoid alloys. So that is the difference between your eutectoid as well as the hypoeutectoid alloys. And complete microstructure view, if you see here, the white, what are the white patches you are seeing here, this is called as a pro-eutectoid. So that means before the eutectoid, how the ferrite looks, and this is the complete perlite. Perlite is nothing but the, again you can clearly notify that if you see the alternate layers arrangement by colonies like that, then that type of things are called as a perlite. So here you have perlite. So this is the combination of perlite. This is the perlite. So visually you can see the arrangement of the atoms inside the material, and you can say where is the perlite or where is the ferrite or where is the cementite with the help of the microstructure. So that is why the study or the development of the microstructures are very, very important when you draw the phase diagrams. Okay, so in this session we have discussed about the iron carpet diagram, iron carpet phase diagram, and what are the different types of phases are available in the iron carpet diagram, and also how are the developments of the microstructures inside the iron carpet phase diagram, and how to draw the microstructures of each type of element in the iron carpet diagram, and what is the importance of these developments of the microstructures, studies of microstructures, and what are the applications, okay, of these iron carpet diagram for selection of the material for any type of applications. Okay, thank you for this session.
Like, share and subscribe. Hit the bell icon for more updates.